Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to day 58 of NL Math Man's Math Help Streams. Here we are. We are on the end of week 12. Boy, oh boy. The final day of week 12. After today, we've got five more. 5 more days of classes. Five more, well, for me anyway. Like the students, I guess, a lot of y'all are transferring. By the way, those of you who are transferring, there will be a very important email coming out on Monday. You will need to let me know very clearly, or Jennifer, both of us actually, because we need to forward on any marks that you have in your courses onto our counterparts at Kenmount, right? Otherwise, you're not going to get any credit for any of the stuff that you have partially done, right? Because if I hear from Kenmount like in the middle of July asking me what your marks are, I ain't gonna know because I'm not going to be checking my work email because I'm not going to be employed. So, it's right. Like it's going to have to be done beforehand. So you're going to have to let me know like directly if you're going or not. Okay. But anyway, I'll send out an email about that. And I don't think anybody, I somehow doubt anybody it's relevant for is even hearing this right now, although they might be, maybe in the future, right? Today now, we do have a very nice picture here behind me, right? Another one of that used to round out a week of beautiful pictures of the puppers, right? We also have a title for the first time this week. I haven't thought up a whole lot of those titles, right? Today we are twirling around, right? We're twirling around with this familiar parable, right? Parable, not parable, parable, like a story, right? And we're weaving around each new experience, right? We're recognizing, not recognize, recognizing, right? Because Maynard, you have to keep your verb tenses constant. We're recognizing this as a holy gift and celebrating this chance to be, you know, alive and breathing, yeah. This chance to be alive and breathing, yeah. Dun, 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 dun. I gotta stop. I gotta stop that before I get DMCA struck. Right? They're like, wow, is the entire band of Tool in his house? What is going on? We got the algorithm is just going to go bonkers. It's going to be muting me all over the place. Boy, oh boy, boy, oh boy. Yeah, I mean that's the lyrics to Parabola, the song by Tool, right? Because we're going to do some parabolas today, right? You know, we're going to be embracing this moment. Remember, right? So we are eternal. We are eternal, and all this pain is an illusion. I really don't think that song has got a whole lot to do with parabolas, to be perfectly honest, right? I've got a feeling that it was mostly just Maynard making like a pun on the fact that parabola sounds kind of like parable, because the song actually mentions parable. Now I'm sure some like Tool superfan will be able to tell me that no, it's actually because it's a cyclical kind of thing where it goes up and then it goes down. Maybe there's some sort of like small little nuance. Why do they call it Xbox 360? Because when you see it, you'll turn 360 degrees and walk away. That's right. I mean, you'll try. You'll try, right? But when you turn 360 degrees, you'll walk into it, right? They'd have to call it an Xbox 180. Maybe that'll be the next one, right? Instead of Xbox, whatever it is, Xbox mini fridge, right? Instead of Xbox mini fridge, they'll call it an Xbox 180. Why would you walk into it? Why would you move? Ooh, that's a good. I mean, you moonwalk away. There you go. Now that makes sense. Turn 360 degrees, you pivot, then you moonwalk backwards. I like it. That's good. Yeah. That's a very small change to the copy path that would make it work. Because you'll turn 360 degrees and moonwalk away. There we go. Yeah. I like that one. Why would you walk into it? Well, I mean, if you walk forward. I mean, I guess you could walk over it, I suppose. It's only small, right? It's just a console. Can I please listen to you? Okay. Yep. I'm trying. Is my mic working? My mic is working. Yes, moonwalking away is perhaps the best way of doing it. But today I am going to be talking a bit about quadratics, right? We're going to get into the order and the equations. It's not the degrees that matter. Well, it kind of is. I mean, this is a math stream, right? So like the degrees are the degrees are really the part of that sentence that I'm going to be focusing on, at least for my purposes here, right? Because being very pedantic about angles, right? The sentence said walk away. It did. It did. Yeah, but you had to walk over it. I suppose you would be walking away eventually, right? But for the first step or so, you're going to be stepping over it. English takes precedence over maths? No. No. And anyway, even with the English, right? You can turn 360 degrees and walk away. That's true. So you could just pivot in spot and then walk off in a totally different direction, right? Perhaps you could, right? But why did you do that flourish then? Why would you spin 360 degrees? It seems to me like the copy pasta really just like it seems like you're celebrating the Xbox at that point, which kind of defeats the purpose, right? If you did this little like pivot and pirouette and spin before you walk around, deflex on the Xbox. Okay, it's like a flex box. There you go. Okay, sure. You're sort of using its own name against it. You're showing, yeah, I know what 360 degrees are. And then afterwards, I'm going to walk in a totally different direction, right? So maybe in total, I'm going to turn like 540 degrees. But you don't tell the Xbox that. I see. Okay. I mean, it's true. You could turn 360 degrees and then continue to turn more than 360, right? To be extremely pedantic, it doesn't say you turn only. You gotta come. Xbox is on fire. Okay. Well, it's red ring of death. We call that, right? You know, don't wrap your Xbox in a towel. Bye for now. Yes. See you later, Charles Barkley's ghost. Although I don't think Charles Barkley is dead, right? Like, I don't know. Hmm. I guess a living person could have a ghost too, right? I I guess. I don't know. Is there precedent for that? Someone who is both living and a ghost? Hmm. That's a good question. I guess like alternate universe versions could be dead. That makes sense. What about Gnarls Barkley? Okay. So over here to the side, right? We do have some of the topics that I'm going to get to today. Like I said, quadratics. We're going to talk about the order and the equation. The order is just it's two. There you go. There's a hint. The order of a quadratic is two. Um, we're going to graph some parabolas. We're going to sing a bit of Tool. Then we're gonna butcher a bit of Tool, and then conditional probability down below. Calais, that'll be for your course. So I'm just going to briefly go over mutually exclusive events and dependent events, which I know conditional probability isn't really mutually exclusive, but they're tied together, of course, right? Okay, yeah, let's just bounce on over here. So Betty Ann, this is going to be so this is the start of your next unit on quadratic functions, right? So it says here on the side the highest power of all quadratic functions is 2, right? Because that's what makes it a quadratic. Well, how about instead of just reading off what's on the sheet here, how's about I just write out some notes for you. So this is math. Oh, that's not a 3. It's a 2101, 2101B unit 3. These courses really drag on after a while, don't they? Like you'd think after doing like, you know, 2 full units and 2 tests, you'd be on to at least another course, right? You know, this is how the academic program works, rather. Um, Actually, quadratic is a term for an equation where the highest power on a variable is 2. Right? So the base form of quadratic, or the basic. Okay. So the basic form of a quadratic is y equals ax squared plus bx plus c, where a does not equal 0, right? Now, you don't always see this written out in the definitions, but it does make sense that a can't equal 0, right? Because if a equals 0 here, well, then this term just disappears, right? So a quadratic is an equation where the highest power on a variable is 2, and we can see here, right, the power, or the exponent, on this x is a 2. Okay? So if this coefficient here, the a, if that was 0, well, then this whole thing becomes 0. So it's kind of irrelevant to write in, right? Because I could add a 0x cubed and a 0x to the 4 onto this, and it still wouldn't affect the graph any, right? So this is true. It's just kind of a little bit of throat clearing, but we do kind of still need to say it, especially in a perfectly accurate definition like this. And I'm not just wasting my breath for this. That is exactly one of the questions that you're asked. I think it's question 4 on the very first page. This page down here, I'm pretty sure question 4 on that page is actually just to explain what I just said. That a can't be 0, because if it was 0, this whole term will be 0, and then we would just have a straight line, because the highest remaining exponent will be 1, which is over here. Okay? So these three coefficients, the a, the b, and the c, those can be any number. Those can, well, the b and the c can even be 0. Right? So let's say here. You'll see later on a bit more about turning points. Now, turning points in a function, the number of turning points that a function has is always one less than the maximum degree of the function, right? So a straight line has a degree of 1 because the highest power on an x is 1, right? So, and it has 0 turning points. A parabola, or a quadratic, right, has 1 turning point, right? So then the most basic of parabolas, I'm just going to draw it freehand, so it's not going to be very accurate, but that is sort of the most basic one, right? So that would be kind of y equals x squared. Now mine's a bit skewed. It's not quite even across here because I just wrote freehand. But if we wanted to see a much better example of it, hold on just a quick second there. Okay, so let me just go over to my Chrome window here. Wait for that to boot up. So this is Desmos again, right? On Desmos here, of course, we can graph out any of these quadratics that we like. See over here, I've just graphed the basic one, y equals x squared, and this is it, right? And quadratic is not really all that complicated. It's not. It is a bit annoying to draw them freehand, and unfortunately, when you're drawing a quadratic like this, even the most accurate drawing by hand is always going to be off a little bit, because what you've got to do is sort of plot out several points. Usually we do like 4 or 5 points on a quadratic, and then we just freehand sort of draw a curve along them as best we can. So you're never going to be perfectly accurate drawing it by hand, but the points that you plot can be accurate, right? So let me I'm not going to quite do everything in the same order that it's done on this page here, but it is important to know a few different things and the ways to find a few different properties of a quadratic like so, right? So when we're graphing a quadratic, we graph it by generating a table of values. Okay, so for y equals x squared, what we can do is we can pick several different values for x. Say I pick -2, -1, 0, 1, and 2 for x. Now all we're going to do is we're just going to take those values and substitute them into this formula. So for example, this is the general way that we write it out. I know that it's a little bit more difficult to start off in the negatives, but all we're doing is just y equals -2 squared, so then y equals 4, right? Y equals -1 squared, so y equals positive 1. And you're seeing, I think now, why a quadratic is going to be kind of mirrored, right? Because a negative squared is the same as a positive squared. We, of course, know that 1 squared is 1 and 2 squared is 4, right? So we see that if the x is negative or the x is positive, the y value here is going to work out to be the same value, right? And that just makes sense when we think about what this, what this equation represents, right? It represents us squaring it. Now, let me take a quick look down through here. Right, there's another part of this that might be relevant right now, and that is finding the vertex, right? Sorry. So we find the axis of symmetry by finding the vertex. Now, for this parabola here, or this quadratic, right, the axis of symmetry is just the y-axis here, right? Because we haven't taken it and slid it in any direction, right? This one is just sort of right here in the middle. But the axis of symmetry is a good way of determining where we should start, right, for graphing our points, or finding a table of values, rather. So when we're finding a table of values, we should find a few values from both sides of the vertex, right? Because what we're doing when we're finding a table of values is we're trying to focus on the most relevant, sort of the most important part of the quadratic, which is the turning point, which is sort of around here, right? Because in order to graph our quadratic as accurately as possible, we would like to have a few points to the left of our vertex and a few points to the right of our vertex. Now, in a quadratic that's as basic as this one, y equals x squared, we know from the start that our vertex is going to be 0, right? Or the x coordinate of our vertex is going to be 0. But how do we know that? How do we know that by looking at it? Well, we can use, like I said, we can use this formula here. Imagine we had a totally different quadratic, right? One that actually had some other values in it. Say we had y equals 2x squared plus 3x minus 4, right? Say that was the one we had. Now we know that our first term, this is going to be a. Now, I shouldn't say first term, actually. That's a way of getting students into a trap. It's not really our first term, that's our a. It's the term, it's the coefficient on the x squared, right? If the order of these were switched around, like it was the linear x first, and then the x squared, and then the constant, it doesn't matter. It doesn't change which one's a and which one's b and which one's c. A is always the one that's multiplied by the squared. B is the one that's multiplied by the linear value, or the variable with an exponent of 1. And then the c, or the constant, is always the one that's by itself, not multiplied by any value, any variable at all. So here, if we wanted to find the vertex, well, the x-coordinate is going to be negative b, right? So negative b is going to be here, negative 3, divided by 2a. So it's going to be divided by 2 times 2. So we know that that's going to be negative 3 over 4. Okay, and that's where our vertex is going to be for this one. So let's go back over to Desmos here, and let's graph it. Let's graph it and see if that is actually the case. Okay, so back over here. Apologies, I still don't have. I gotta lean in over to reach my keyboard. So it's going to be y equals 2x squared. So I like how Desmos keeps popping it up there as we're going, right? 2x squared plus 3x minus 4. Okay? So there, the blue one now, the one that we just graphed, this is that parabola. 2x squared plus 3x minus 4 right here. Now, if we look down here, we see, hey, look at that. Look, that's the vertex. Desmos very kindly gives us a point for the vertex right at the gate, so we know where it is. And it tells us that that point is going to be negative 0.75, right? And negative 0.75 is, of course, what we found back over here, right? Negative 3 over 4, negative 0.75. The reason we don't need to use the C coordinate in here, right, is basically because this coordinate here, or this value here, sort of widens or narrows. Actually, this one sort of widens or narrows our function, right? Let me, yeah, this is a good point to get off onto this topic, because this is something I did want to talk about as well. Let's pop back over to Desmos for a second. Now, Betty Ann, your course doesn't get into this right now, but you do get into all this stuff in the next time you're looking at quadratics. So I think it's really good part to tell you right now what each of these terms do, because this topic does come up again. It's the first topic of the grade 12 ones, so you'll have one course away from it, and then as soon as you get into 3101A, you're going to be right back into this topic again, just you're going to be looking at it in more detail. So I think that right now is a good time to explain what a few of these terms do. Right? So you see this 2 here, right? Like if that becomes a 1, look at that. All of a sudden the graph is a lot wider, right? It does shrink it a bit. Like it does change where the vertex is somewhat. But you notice if I go make it a 2, it gets a lot narrower. 3 is narrower still. 4 is even narrower still, right? Whereas this one over here, this one on the linear, say I take that and made it a 1. Look at that, right? A 3, a 1. Oh, sorry. I just deleted the X instead. You notice these ones don't, it's hard to see exactly how it's going to go, right? So it does go down a bit and to the left, but it does mostly, well, these two terms together, the A and the B, govern sort of where it's going to be vertically. But if I look at this last term, this minus 4, right? Say I change that to just minus 0, like that, okay? Or say I change it to minus 3, or minus 4, or minus 5. You notice that it's just kind of moving up and down the page, right? That term, actually, you'll notice that the vertex stays in the same x-coordinate, right? Because if it's a minus 3, my vertex over here is still negative 0.75. If this changes to, say, a minus 5, my vertex over here, oh, it's still negative 0.75. If it changes to a minus 1, that's still negative 0.75, right? So that's why the C term, or the final term, we don't actually need to use that when we're figuring out what the x-coordinate of our vertex is. Oh, seeing the edge of my keyboard here. Okay, was I dropping frames or then, or buffering? No drop frames. Okay. Well, my stream does seem to be a little bit lagging behind me here. But anyway, so now, basically, we know that negative 3 over 4 is going to be the x-coordinate for the vertex of this one. So if we were to try to make a table of values in order to graph this, we should pick some things to the left of that and some things to the right of that, right? So I don't have a ton of room over here, but just to show you sort of how it would go down, right? If I had an x and a y, I would want to pick, say, I don't know, negative 3, negative 2, negative 1, 0, 1, and 2, maybe. I always tend to pick whole numbers for these. Now, yeah, I've totally run out of room here on this one. So I'll tell you what, I'll just show over here the way that we would go about generating a table of values for a parabola or a quadratic like that one. I don't want to use those terms interchangeably, but the parabola is the shape on the graph, whereas the quadratic is the type of equation it is. So it's not really splitting hairs. Those are sort of relevant differences in the terms. And for some reason, my stream has gotten quite a bit behind reality here. So if you say something in chat today, it will perhaps take me a little bit to respond. In meat space, in the real world over here, or I've had to talk about this before, meat space is not the real world anymore, right? In 2020, our real world is the online one. The rest of it is just needless trappings. But But anyway, it'll take me a little while to respond if you drop anything in chat, just because yeah, there appears to be a bit of a delay today. Right? So then it's a bit painstaking to go about generating a table of values. But you see over on the side here, right? So this is in this next page that we were looking at, this is exactly what they did here. So they generated a table of values for this quadratic. I'm generating a table of values for this other quadratic that I just thought up off the top of my head. But it's totally fine. Like negative 3 squared is 9. So this is 2 times 9 or 18. And this is 3 times negative 3, so that's going to be a plus a negative 9. That's going to be a minus 4. So that's going to be 18 subtract 13, so that's going to be 5. So we know that when x is negative 3, y is going to be 5 here. And it is kind of painstaking, but we are just going to go through and do out several more instances like this. Y equals, that's 2 times 4 is 8, minus 6 minus 4. So y is going to equal negative 2. Right? Y equals 2 times negative 1 squared plus 3 times negative 1 minus 4. So y is going to equal 2 minus 3 minus 4. Y is going to equal negative 5. Right? When it's 0, 0 is quite easy, isn't it? Right? Because if we were to take this one and make parts of it 0, y equals 2, 0 squared plus 3, 0 minus 4. Well, that's just going to be y equals minus 4, clearly. Right? And then if we did 1, well, 1 is just going to be y equals 2 times 1 squared plus 3 times 1 minus 4. So that's going to be 2 plus 3 minus 4. So that's going to be a positive 1. Right? And then y equals 2 squared plus 3 is 2 minus 4. Y equals 4 times 2 is 8 plus 6 subtract 4. It's going to be 10. Right? And let's go back over to Chrome here. Let's go back over to Chrome and see if what we found pans out. Right? I'm going to have to zoom out a little bit. So let's see over here. What is this? There we go. Yeah. 2 and 10. I'm not getting it directly on there. There we go. There it is. Yeah. That's right. See, 2 and 10 was correct. How about 1 and 1? Is 1 and 1 correct? Oh, look at that. 1 and 1's right there. Hey, right? 0 and negative 4, also correct. Negative 1 and negative 5, right there. Right? So we see it does indeed check out. And if we were to try to graph that ourselves, what we would do is just plot each of those points on a coordinate grid and then just join them up as best we can. We're not going to join them up with straight lines. We're just going to try to put a curve through them as best as possible. I believe we'll be doing some of that today on some of the questions that I picked out to go over, but I just wanted to explain a bit about the basics behind quadratics before we got to that point. Okay, but now in the book, I would like to do a few of the questions that you were assigned for your notes. Right, so I'm going to do page 324. So let me bounce over here, page 324. Let's do question 2. Okay, which of the following relations are quadratic? Explain. Okay, so this is going to be math 2101B, unit 3, page 324, question 2A. Okay. So, how are we going to tell if these guys are quadratic? Well, is this one a quadratic? Remember, a quadratic equation has to have x squared in it. Basically, that's all it really means, is that there has to be, and x squared has to be the maximum. That's the biggest power of x, has to be x squared. So this one is no, it's linear. Right, because this is just y equals 2x minus 7. Here the largest power of x is 1. right? Because the ones are, of course, unwritten. We don't write the 1 in here in the corner, but there is indeed a 1 there. And since the highest power of x is 1, well, then it's a straight line. It's not a parabola. For b, then, we have y equals 2x outside of x plus 3. So we just go through and multiply this out and see what that is once it's all multiplied out, right? And we know this is going to be y equals 2x squared plus 6x. So yes, this is a quadratic, right? Because it has this 2 here. That 2 in the corner, that means this is a power of 2, right? Or a second order, right? So it is indeed quadratic. Let's see, C here. C is y equals x plus 4 squared plus 1. Now, we don't really need to FOIL this out to know that this is going to be a quadratic, but I'm going to go ahead and FOIL it out anyway. Right, just to sort of model good behavior, I guess. That's x squared plus 8x plus 16 plus 1, or y equals x squared plus 8x plus 17. And this is, of course, quadratic. Right? Yeah, let's keep going with this one. Let's get all of question 2 done. Why not? Part D. I'm going to sort of cram these ones in here a little bit, because this one is y equals x squared minus 5x minus 6. You know, this one is, of course, a quadratic because it has x squared right there. Right? There we go. It's got x squared and it's got no x cubed or anything like that. X squared is the largest exponent. Now, mentioning that about x squared being the largest exponent, that's why I wanted to keep on going here, because for 3, we've got 4x cubed plus x squared minus x. Now, this one is cubic, so this one's not quadratic because this has an x to the power of 3 in it. Right? So when it has an x to the power of 3, you'll notice this one has 2 turning points. So this one is kind of going to go like that. Right? It's going to be sort of like a sideways S sort of shape. Right? That's because it's got the cubed up there. And f, you're going to notice if you multiply f out, f indeed will also be cubic. Right? Because for f, we're going to have y equals x outside of x plus 1 squared minus 7. So that's going to be x outside of x squared plus 2x plus 1 minus 7, which is going to be x cubed plus 2x squared plus x minus 7. This one is no, it's cubic as well. Okay, question 3 here. I want to do that one as well. That one's a little bit different than what I was just talking about in the first bit there, because it was asking us to state the y-intercept for each equation, each quadratic relation in question 2. Well, how do we find the y-intercept of a straight line? Right? What is the y-intercept? Well, the y-intercept remember from looking at straight lines, y-intercept is our y value when x equals 0. So that was what it was in straight lines, and guess what? That's what it is in parabolas as well. It's what it's going to be in every type of line that we look at. No matter how many curves it's got, the y-intercept is always the y value when x is 0. So easy peasy. All we got to do is go back to our quadratics, like say b up there, right, is y equals 2x squared plus 6x. We're just going to put a 0 in for each x and then see what it works out to be. Y equals 2 times 0 squared plus 6 times 0. Y equals 0. There we go. It's not hard. Right? You're going to find that it's going to be the constant. It's going to be the constant every time because that's the only thing that's going to be left over after we make all the x's into zeros. Right? So say for part C up there, part C is y equals x squared plus 8x plus 17. Right? So y is going to equal 0 squared plus 8 times 0 plus 17. So y equals 17. It's like I said, right? It's going to be, I think that's relatively straightforward to see why that happens. right? Because knowing that a y-intercept is the y value when x is 0, right? Then once we set x to be 0, we're only going to get, and we only get one value for these, right? Because quadratics like these are indeed functions. Functions meaning that for every given x value, there is only one y value. However, the inverse is not true. For any given y value on a parabola, there's one, two, or 0. But anyway, we'll see a bit more about that, in a bit. Question 4, like I mentioned earlier, question 4 says explain why the condition a does not equal 0 must be stated when defining the standard form. Well, like I said at the beginning, right? If the leading coefficient is 0, well, then the x squared is irrelevant, right? Because 0x squared, you've got 0 of every level of x that you don't show there, right? Because 0 times it is 0. So it's no point in writing it in. So there has to be a non-zero amount of x squareds in your question. It can be negative, of course, right? It just can't be 0. It can't be literally none. Does the parabola open up or down? Explain how you know. I'm not super actually, yeah. Let's do that. Let's do that a little bit, and you'll see maybe the consequence of one of the terms that we have here, right? So this is a decent one to mention. So for question 5 then, 5a, we have y is equal to x squared minus 4. I'm just going to write out a few of these. I'm going to write out 2 of them here, just so I don't need to flip back. So I literally have them in front of me, so I can put them on the screen when we go over to Desmos. Okay. Chrome window, here we go. So let's make another new one over here. So we're going to have y equals x squared minus 4. There we go. So that's this green one. Actually, let me disable the other two so they're not cluttering up our screen. There we go. Right? So y equals x squared minus 4. That one opens up. Let's try that other one. Oh, let's add in another one. It's easier just to click there to add. So this is going to be y equals negative 2x squared. Shift 6. Yes, y equals negative 2x squared plus 6x. That one's opening downward. What's the difference? What's the difference between these two guys that makes this happen? Well, how's about I just go up here and I tinker with this a little bit. Let me put a negative in. Whoa, it switched. Positive, negative, positive, negative. Right? So it's just it's the sign of the a coefficient determines if it opens up or opens downwards. It opens up if a is positive. It opens down if a is negative. Right? That's all there is to that one. Oh. I had forgotten that I had that speaker on. Let me mute Reno my usually I just have headphones. So parabolas open up if a is positive. Right, so the leading coefficient, if it's negative, it opens downward, right? But again, I call it the leading coefficient, but it's not really the leading one. So if you look over at C here, right, the A term is still this positive 3, right? Even though the constant is written first, it doesn't matter what order it's written in, because we know these terms are either added or subtracted, right? Which means it's kind of the order doesn't really matter for those guys. What matters is the power of x that it's multiplied by. Okay, so I think that's a decent look at that. I did also want to look at page 333, questions 1, 2, and 7. Now, what were those? Oh, okay, yes, good. So we're going to get into a little bit more of the number crunching-y stuff, because there's a fair bit of just like number crunching math that we do with parabolas other than just graphing them as well. It's a relatively big topic, and like I said, you do get back at it later in your program, so this is not the only time that you're going to be doing these ones. 2101B Unit 3, like so. That's 2A. All right, so f of x, excellent. So they're writing it as f of x. F of x, for our purposes, f of x is just the same as y. That's how we read this, right? I know it's like a italic x or whatever. Actually, I should have used more of an italic x for it. But this is f of x, meaning a function that depends on the value x. I believe you saw this notation in an earlier course as well, just to know that it's basically just the same as putting a y there. You'll sort of see if you go on and do calculus and stuff like that, you'll see y for the notation later on, like for derivatives and integrals, why we write things as f of x instead of just a y. Well, actually, that's not quite true. No, you can do dy over dx too. Never mind. What do I know? It is kind of just an alternate notation, really, for our purposes. Right? So the coordinates of the y-intercept, well, we know that the y-intercept is the y value when x equals 0, right? So just like we saw before. So I'm going to go ahead now and make x equals 0. So we call this then f of 0 equals 2, 0 squared plus 8 times 0 plus 8. So not surprisingly, f of 0 is just this 8 that's left over there, right? Now state the coordinates of two additional ordered pairs for each function. Now, this links back to what I was just talking about, how because a parabola is a function, there is only one y value for any given x value. However, unlike a straight line, the opposite is not true, right? There might be no x values for a y value, or there might be two x values for a given y value. So when we're trying to find, what does that mean for what we're doing here? Well, when we're trying to find coordinate pairs, what we should always do is we should always set x to be something, then solve for y. If we set y to be something and then try to solve for x, it's going to be a lot more work. We're going to have to factorize, we're going to have to use the quadratic equation, and we could end up with an answer that is actually doesn't work because that given y value is actually not part of the parabola. Right? Because if you look over here on the side, you'll kind of see what I'm talking about, right? Actually, I should write this out over here. Yes, this is a really good point. For parabolas, domain is always x is all real numbers, right? Because you look over here, even though the parabola starts going a lot steeper as it goes higher, or as this one, as it goes lower, it gets steeper, it still continues infinitely left and right. You notice these arrows on the end here, that arrow there, or this arrow here, or this arrow here? That's telling you that it continues infinitely in this direction. And it mostly goes up, but it also goes left and right. And because it's infinite, even a little bit of slant to the left or a little bit of slant to the right, eventually it'll hit every single x value there is. Right? So any parabola will always have a domain of x is all real numbers, like unless you're specified, like unless you're given limits where the parabola literally stops. But from the quadratic over here, you will always have the domain be all real numbers. But the range can have a min or a max. Like if we look at this one over here, right, we see that the range is from -2 up, right? Because -2 is the minimum value here, right? And we find that, we can find that value by getting, first we get the x value of the vertex, and then we get the y value of the vertex. We'll see that now in a second, because I guess seeing I'm introducing it here, I'll go on and do question 3 as well before I'm done with this topic. But the reason that's important for this question is because, say, for a straight line, if we wanted to figure out points on a straight line, we could choose either y or x and fill in any given number and then figure out the number for the other one. But for a parabola, we can't really plug in y, because if we do, we could end up just wasting our time, right? Because imagine if you had the equation for this one and you tried to set y to be -3. Well, look, if y is -3, we go across here, there isn't a single point on y equals -3. Or if we chose y as +3 and did it, we would get 2 answers. We'd get that one there and that one there, right? But for any x point, there is only exactly one y point because it is a function. So for question 2a here, what I'm going to recommend you do is pick an x value. So I'm going to pick, say, the x value of 1, because 1's an easy one, right? 2 times 1 squared plus 8 times 1 plus 8 is going to be, obviously that's 2, and that's plus 8, and that's plus 8, so that is 18. So we know that, right, x comma y, we have 1 comma 18 is a point on this one. We also know from up here, right, that 0 comma 8 is going to be a point on it. But it asked us to find 2 additional ordered pairs. So let's get one more, because that's what the question is asking us to do. So how's about I pick a tougher one? How's about I go f is going to be now -3? It's not exactly that much tougher. But, you know, I want to show a few sort of different types of examples that we can get, right? So -3 squared is, of course, +9. +9 times 2 is an 18. So a 8 times a -3 is going to be a -24. That's going to be a +8. So we're going to have 18 plus 8 is 26. 26 minus 24 is going to be a +2. So another point we have is going to be -3, +2. Right? So that's just the way then that we can find points on the quadratic, and the best way to do it, like I said, is to pick an x value, not pick a y value. Sort of the same deal over here for 2b. I'll go down through this one as well. So f of x is equal to 4x minus x squared. This is a good example because here now the order of the terms has flipped, but the order of the terms flipping doesn't matter anything at all, really, right? Because the y-intercept is still the y value when x is 0. So we're still going to do f of 0, and that's going to be 4 times 0 minus 0 squared. So that's going to be 0. So we know that one point on this graph is going to be 0, 0. We know that one, right? So then, just like I said before, let's pick some x values. Let's pick easy ones. Let's do 1 again, right? Why not? 1's easy. 4 times 1 minus 1 squared. And here now you'll notice that the negative is not part of the square, right? If we look over here, we see that the negative is in front, right? So that means even after we square this 1, we're actually not squaring the -1. We're just squaring the +1. So it's still going to be subtracted, right? So f of 1 is going to be 4 minus 1, or f of 1 is going to be 3. I'll keep my writing consistent here. So that means when x is 1, y is 3. Okay? So let's pick a negative now. Let's do f of -2. It's going to be 4 times -2 minus -2 squared, right? And this is how we're going to write it out now, because our -2 is the value we've chosen, so that's what's being squared. But this negative here, in between, that's not actually going to be part of what we're squaring. So now we're going to have f of -2 is going to equal -8 minus 4, minus a +4. So f of -2 is going to equal a -12. Right? So that just gets us the 3 points on there like they were asking for. Yes. So like I said, I will. Yeah. Let's quickly do question 3. And we're doing. This is quite a fair bit of time to spend on this one topic there. But Betty Ann, hopefully you're finding it useful. So I will carry on and finish this one. Oh, hey Slayer Darth. Yeah, it's going pretty well. Like I mentioned earlier, my uh, I might seem a bit slow in responding today because for whatever reason my stream is lagging way behind reality. Or wait, what? No, that's right. But with my thesis of like the stream being reality, that sort of throws a monkey wrench into that one, doesn't it? But yes, the stream's lagging a bit, and I don't really want to bring it down and back up again to fix it. So this is 3a here. So for each function, identify the x and the y intercepts, determine the equation of the axis of symmetry and the coordinates of the vertex. New video game dropped today. Ooh, oh, that was Last of Us Part 2, right? Yeah. I haven't played Last of Us Part 1. I do see a lot of streamers that I watch are playing that one today. Like, I look over on the left-hand side of my Twitch screen. Yeah, like everybody is playing Last of Us Part 2 right now, pretty much. Yeah. That's a pretty cool game. Like I don't have a PlayStation, so I haven't played the first part of it, but I do dig games um, that are trying to do something new with story in games. Although I gather Last of Us isn't really trying all that new stuff from like a narrative perspective. It's just a good version of like the kind of narratives that already exist in games. Correct me if I'm wrong. I don't know if I'm. Yeah, I haven't really watched anybody or played it very much. I think Twitch is prioritizing bandwidth for the bigger streamers. Yeah, it's entirely possible. It could just be. It could just be my Bella Lion, just having a bit of a hiccup today too. Uh, okay, so for 3a, let's see here. Identify the x and the y intercepts. Well, the x-intercepts, now we're not given the equation of the function here, but we can just see these off the graph, which is what we're meant to see. X-intercepts are otherwise called the roots. And Betty Ann, it's strange to me that we um, haven't actually talked much about the roots yet in the way that this course is introducing it to you, because generally that's like the main thing that we do when we're solving quadratics is we find the roots. What the roots the values of the x-intercepts. Now there's either 0, 1, or 2 x-intercepts, but for both these ones we've got 2, right? So we see that the x-intercepts of the roots are going to be 0 and positive 2, right? Because we can see those right here and right here. The y-intercept is only ever going to be 1 y-intercept, but there's always going to be 1, exactly 1. And here that's 0 as well. Then the domain, like I mentioned before, the domain is going to be x is all real numbers, right? We know that the domain for any quadratic is always all real numbers, unless it has some sort of like artificial limit put in. But anyway, we're not going to be dealing with that. And the range, now the range is relevant here, right? Because as we can see, the range is y is greater than or equal to -2, and then y is all real numbers. Generally, we're always gonna have this part, but I would like you to be very thorough and to write out this YER thing as well. Although it's like a double line, sort of thick R, and this is a curvy E, kind of like a euro symbol, but still, I'll just say YER. Yer. That's good enough. For B, x-intercepts are going to be, that's going to be a -1 and a positive 6. Right? We can see those right here and right here. I don't know why my cursor turned into the text cursor there for a second. The y-intercept, we can see that one right here. So the y-intercept is going to be a positive 4. Domain is going to be x is all real numbers. And then the range is going to be y is less than or equal to, oh, it's a little bit above, isn't it? Let me zoom in a bit. Oh. I don't think they meant for you to zoom in 500 times on the page, but as we can see here, that is definitely a bit above the 9, right? Because the 9 would be right here. So what do we call that? 9.2, maybe? So y is less than or equal to 9.2. Y is all real numbers. Either way, for this question, we're not given a formula, so you're not going to be expected just to generate a formula. At least not yet. You're not going to be expected to sort of generate a formula based on what we're showing here. Also, because just knowing the roots, you can't actually generate a formula because given two roots, there still is an infinite number of parabolas that you could have, right? Because you could have the same roots be super shallow or super steep, right? So just knowing the roots doesn't tell you, definitely does not tell you what the actual equation of the parabola is going to be. Anyway, Betty Ann, that will be, I think that's a fair bit there on quadratics and parabolas and also tool lyrics that have very questionable amount to do with parabolas. Seems more of a pun on parable, more so than parabolas. Which topics are you tackling in today's stream? Yes. Yes, so next up, we're going to be doing conditional probability. So that's mutually exclusive events and dependent events. So Calais, that is for your course. Let me just take a sip of my tea here. Hydrate. It's a nice default Tetley. Don't have any of the Earl Grey anymore, like I used to talk about early on in the stream. But just plain old Tetley tea, right? That's the good stuff. Switch on over here. Okay. Yes, you're very welcome, Betty Ann. Hope that helped you. And as always, let me know if you have any other questions. I'll get to those. I'll get to those Monday, of course. Right. Not going to do a weekend stream, even though that would push me up to 64, which would be a nice square number to end on instead of 63. But I'll deal with that. Ending on a prime number is good. Earl Grey was a prime minister. No, I did not know that. I know that starship captains prefer to drink Earl Grey. I do know that, at least cultured ones, right? Charles Grey, the second Earl Grey. Oh, okay, yeah. So he was both like a nobleman, I guess, with the Earl title, but then also a prime minister. I know there was a prime minister with the same last name that I have. I guess I shouldn't dox myself to basically tell my full name on stream, but yes, I do share a last name with the prime minister. Though the clan that had my last name, came over from the West Country as fishermen and settled in Newfoundland. So not exactly the same stock that leads to a prime minister. Quite, just people that sailed from Bristol and decided to make their fortune in this, rock stuck in the middle of the Atlantic and just pull cod out of the sea for a living. Was the prime minister when slavery was abolished throughout the British Empire in 1833? Oh, excellent. Yeah, that's pretty cool. Yeah, British Empire did have slavery until quite a bit later than some people realize, right? But it was perhaps more prominent in some of the some colonies other than others, I guess. Some colonies more than others is what I'm trying to squeeze out here. Past acts to reform Parliament. Oh, excellent. Yeah, I should look that up. I do. I am definitely a history nerd for that kind of thing. So that's really interesting. Yeah. This is math. What is this? Slave trade was abolished in 1807. Oh, okay. Slavery was abolished in 1833. Okay, so they couldn't trade more. I see. 3101. What is this? Math 3101A, Unit 3, I believe. Yes, that's right. That's right. So mutually exclusive events, all that means is they are events that cannot both occur, right? So it's not a super complicated sort of notion, right? Venn diagrams, yes, Yes, we are back indeed to the Venn diagrams. So mutually exclusive events, like I'm saying, are just this is not a particularly difficult topic. I just want to sort of get this one out of the way before I get into talking about the conditional. Conditional is not difficult either. It's just sort of it's dependent events then, right? Instead of mutually exclusive. But as we see down here, as we see over here, right? Mutually exclusive. It's just two Venn diagrams that don't overlap. Non-mutually exclusive do have an overlap, right? It's not a super difficult concept, right? So like it says here for the example, eating habits. 62% skip breakfast, 24% skip lunch, 22% eat both breakfast and lunch. Are skipping breakfast and skipping lunch mutually exclusive? Well, no, of course not. You could skip both, right? Just think of it conceptually. Mutually exclusive is like, is it going to rain or not rain tomorrow? Thanks to me, you know how to solve these now. Excellent. Yeah. glad I'm glad that I could help. That's amazing. Yeah, but like if you think of like a weather forecast, right? You say 40% chance of rain, well, then 60% chance of not raining, right? And it can't both rain and not rain. I mean, I guess in a weird way it can, because it can rain in parts of the day and not rain in others. But that's not what we mean, right? It's either gonna rain sometime in the day, or it's not gonna rain at any time in the day. Two events that do not depend on one another. Not quite. Not quite. No, mutually exclusive events aren't the same as independent events. Independent, and which is something that I am going to talk about now. Yes, so I should write that down as well. Right. Yes. So mutually exclusive events are events that cannot both occur. They do sort of depend on each other, though. Well, yeah, because if they're mutually exclusive, if one occurs, the other one simply can't. Right? Whereas independent events can both occur, but one happening doesn't affect the other one at all. Right? Like for independent events, I could say, it's going to rain tomorrow. I'm going to eat pasta tomorrow. Right? Like both of those things could happen, but one is not really affecting the other one. So those are independent. But what I'm going to get onto today, as we saw at the beginning, there was dependent events. So a dependent event could be, it's going to rain tomorrow or I'm going to barbecue tomorrow, right? And because barbecue is outside, obviously, if it rains tomorrow, there's a lot lower chance that I'm going to barbecue, right? So we can think of mutually exclusive ones, like I said, are things that can't both occur. So that's like it's going to rain and not rain tomorrow. Well, it's got to do one or the other, right? Independent events are two events that could both occur, but it doesn't really matter. One doesn't affect the other, but they can both happen. Dependent events are ones that do affect each other. So if we look back here at this example, skipping breakfast, skipping lunch, and eating both breakfast and lunch, these ones here, to my mind, these sound like dependent events, right? Because you got to imagine that someone who skips breakfast is going to be pretty hungry by lunchtime and is going to be less likely to skip lunch. Right. Skipping breakfast and skipping lunch are not mutually exclusive. Breakfast and lunch take place at different times. Exactly. Yes. They are not mutually exclusive because you could skip both. Right? Maybe it's just a person who doesn't like to eat during the day. Maybe, I don't know, maybe money's tight and they want to save up and just eat for supper. That's a bit tragic, but I mean, it happens in the world. Or maybe they're on a cut. Maybe they're really trying to shed some pounds and they're just avoiding breakfast and lunch, even though that seems like a poor way to do it. Maybe you should eat something for breakfast. But still, these are definitely not mutually exclusive. No. And they're not independent either. of course, right? Because like I was saying, if you skip breakfast, you're going to be pretty hungry by lunchtime. So if you skip breakfast, you're probably less likely to skip lunch. But someone who has a big breakfast, come lunchtime, they might not even be all that hungry, so they're probably more likely to skip lunch, would be my thought. So sounds like skipping breakfast and skipping lunch are going to be dependent, right? So here's solution A. You could skip both breakfast and lunch, as you see when you go on to. Now, like I said, I'm not gonna spend a ton of time on these ones. What I did want to talk about here is conditional probability, right? And there are some formulas for these. Um, to my mind, the formula is almost overcomplicating it a little bit, but we are still going to go and do the formula, right? So so dependent events involve conditional probability, basically. So this B bar A, we read that as B given A. The probability, so the P outside means probability. This is probability of B given A, or in other words, it's the chance of B happening if A has already happened. So we know that probability of B given A for an event like this is the probability of A and B divided by the probability of A. But sometimes it makes more sense to think of these guys as tree diagrams. I think tree diagrams are a much more intuitive way of representing what is happening here in conditional probability. So I'm going to go now and solve a few of the questions from the text that deal with this unit. So like it says down at the bottom, you're asked to do pages 188 to 191. And of course, you'll recall that for social distancing, for the teaching we're doing now, these ones are not required for marks. However, those are going to be the ones that I go over, so you're very recommended to do it, right? And we see over here at the top of the page as well. So this is page 188, very useful page in your textbook. This is basically the same stuff as what I just said, right? If event B depends on event A occurring, the probability that both events will occur can be represented as PA. So the probability of both of them, right? Actually, yeah, this is a good thing for me to write down here because this is just another way to rearrange this formula. So the probability of A and B is equal to the probability of A multiplied by the probability of B given A, right? And this B given A, you've already been doing that. You've actually been doing this all along. So this is not any different than what you've been doing already because we know, say, for example, if we want to find the probability of drawing two specific cards from a deck, right? Say we wanted to find the probability of getting exactly, now let's get a good hand. Let's see here. Here we go. Here we go. The only thing you see, the only card for me, is the Ace of Spades. Ace of Spades, yeah. That's the second metal song I've referenced today. Hey, there we go. I'm on a roll. I'm on a roll. Oh, I've got a real tragic story about Motorhead. Actually, there was when I was in the UK, I heard just randomly just a rumor that Lemmy Motorhead was doing a show randomly, like the Underworld, the tavern in Camden, and that's incredible because I love Motorhead. Motorhead's just such an amazing, intense, loud, just in your face kind of band, right? It's incredible, and that's just the kind of guy Lemmy was apparently. Like sometimes he would just get bored or whatever, and just hasn't done a show for a while, and he would just randomly want to go out and just go to a bar he liked and kick some ass for an evening, right? And I heard about it, but it was on a Thursday night, and I was working like crazy. Had to be up real early in the morning to go to school the next day, and I was like, you know what? Maybe I'll catch the next Motorhead show. It's going to be crammed anyway. I'm going to have to try to get home on a Thursday. I don't want to have to call in sick because I only just started this job. but I should have called in sick. I should have went and called in sick on Friday because it wasn't. It was only a few weeks after that that Lemmy ended up in the hospital, and then the metal world found out that gods can die apparently, which is real tragic. But anyway, that's the show that got away for me was the possibility of seeing one of Motorhead's last shows at the Underworld Tavern in Camden, in a crammed bar on a Thursday night, and I should have went. But anyway, yes, I got off onto that because I dealt out an ace of spades. But say that we had a Calais. The reason I wanted to talk about this was not just to ramble about stories, but to show you that you've already been doing this, right? So what's the probability of getting an ace of spades and the king of spades, getting this exact hand dealt to you, right? Well, we know that the probability of the ace of spades, right, is going to be 1 out of 52. And we know that the probability of the king of spades then afterwards is going to be 1 out of 51, right? And we know it's going to be 1 out of 51 because there's already one card dealt out. So this, knowing that it had to change to 1 out of 51, you are already knowing that you had to do this, right? Because the probability of this happening, giving that was already dealt, means there's only 51 cards left in the deck, right? So this is not really a super complex or arcane sort of thing. It's something that you've already seen a whole bunch of times, right? So say the probability of the ace of spades and the king of spades is going to be 1 out of 52 times 1 out of 51, which is going to be 1 over, can't do 52 times 51 in my head, 2652. So pretty small amount, right? It's going to be, wow. So it's less than 0.1% to get that exact hand dealt in a game of Texas Hold'em, I guess, right? Because it's a 2-card game. Anyway, the suit actually doesn't matter in Hold'em, really. Just ace-king suited is what we would be dealing with. So really it could be, if you wanted any ace-king suited, it would be 4 out of 52, then times 1 out of 51, because it could be any ace, but then afterwards it would need to be the same king as that one. But anyway, I wanted to talk about the ace of spades. The ace of spades. Anyway, that's just to say, just to show you that even though this formula might look different than what you've seen so far, you have been doing this exact thing already. Right? This is going to be Math 2101, wait, 3101A, Unit 3. And we're going to do a few questions on page 188. Yeah, yes, Laird Dorothy, it is some definite missed opportunities there. But, I did what I thought was right. I did what I thought was right for my job and my career and, doing a good job at what I do, which I do, I do always endeavor to do well at the job. But ultimately, calling in sick on one random like October Friday would not have really been a big deal in the end. But seeing that Motorhead show would have been a massive deal in the end. But live and loin, I guess, right? Okay, so Austin rolls a regular 6-sided die, regular 6-sided red die, and a regular 6-sided black die. If the red die shows 4 and the sum of the dice is greater than 7, Austin wins a point. Are the two events dependent or independent? Okay, so let me break out some dice. Now, unfortunately, I only have the one set of dice here, my very pretty dice log, right, that I got for Christmas one year from a friend of mine. But if one die, so one die has the roll of 4, okay? So this die has to come up a 4, like so. Then and the sum of the two dice is greater than 7. Well, that 4 is greater than 7. That 5, that makes it now greater than 7. That 6 makes it greater than 7. Another 6. A 1. Oh, now it's less than 7. Now it's 5. Right? But does the sum of the dice, does that depend on the roll of the first die? Well, of course it does. Right? Because we're still counting. The question is not the first one has to be a 4 and the next one has to be 3 or greater, which is kind of what it is. But the notion is the first one has to be a 4 and the sum of them has to be greater than 7. So the sum of the dice still depends on the first roll. So they are indeed, the events are indeed dependent. Okay, it's the first die and the second die, right? Determine the probability that Austin will win a point. Right. So remember now, a probability like we were just looking at above here. So the probability that the sum equals the sum is greater than, oh, it has to be greater than 7. The sum is greater than 7. Okay, sum is greater than 7 given, right, given that given that red die equals what? Equals 4. So if the red die equals 4, what's the probability going to be then that the sum is greater than 7? Well, how many favorable situations do we have? Remember, because probability is always favorable over total. So 1, that's not favorable because that makes 5. 2 makes 6, is not favorable. 3 makes 7, needs to be greater than 7, not equal to, so this is no good. But 4 works, 5 works, and 6 works. So that's going to be 3 out of 6. Right? So the probability that the sum is greater than 7 if the red die is 4 is going to be 3 out of 6. And the probability that red equals 4 is, of course, going to be 1 out of 6. Right? Because there's only one 6 on the die, right? So the probability of both, remember, because we looked at above, the probability of A and B is equal to probability of A times the probability of B given A. So in this case, the probability of red equals 4 and sum greater than 7 is going to be 1 over 6, right, times 3 over 6. Or I could say 1 over 6 times 1 over 2. So let me just make that 1 over 2 instead. So that's going to be 1 over 12. Right? Let's see, what other ones did I want to do? Questions 2 and 3 are relatively quick, so let's go over those. Question 2 here. Valeria draws from a deck of oh my goodness, these hiccups. She draws from a deck of well-shuffled playing cards, draws another card without replacing the first. Are these two events dependent or independent? Well, dependent. Right, so these ones are, of course, dependent, because depending on what card she drew out first, there's going to be 51 cards remaining, and there's going to be one card that's not in there anymore. Right? Determine the probability that both cards are diamonds. Well, again, right, this is a good example of the fact that you've been doing questions like this already, even though you might not have been thinking about it in these terms, right? Because we know that if we deal out one diamond, like so, right, the probability of the diamond the first is going to be, of course, well, there's 13 diamonds out of 52, or 1 out of 4 first, right? So the probability of a diamond is that. The probability of a diamond given already chosen a diamond is going to be, well, now there's going to be 12 remaining out of 51 in there, right? So then the probability of 2 diamonds is going to be basically both these things happening. So probability of 2 diamonds is going to be 13 out of 52 times 12 out of 51, which is going to be the same as, like I said, 1 over 4 times 12 over 51, which is going to be 12 over 204. Yes, which is going to be it's going to be 3 over 51. Okay, I was just simplifying the fractions down a little bit here, right? Because what we actually have here is going to be 1 over 4 times 12 over 51, and we can cancel those ones and call that 3 and that 1, so it's going to be 3 over 51. To show you kind of what's going on there with the fraction math. I'm sure you've seen fraction math like that before, just we haven't really revisited that very much in the courses that you've been doing here. So just to be very clear about what I'm doing there. So in 3a, she does the same thing again, but she replaces them. These ones are independent. It's independent because the first event doesn't affect the second event, right? Because if she replaces the card, if she deals out, this 8 of diamonds here, and then takes it and sticks it back in, she could get the same 8 of diamonds again, of course, right? So this one is just going to be, see, 1 over 4, because there's a quarter of the deck is diamonds, and then for the second trial, still a quarter of the deck is going to be diamonds, so it's going to be 1 out of 16. Right? Which you would see if you turned it into a decimal, you would see it's a slightly bigger number than this one. Not a huge deal. Now, let's see. I wanted to do. Yeah. Okay. Now it's it's my Friday, so maybe I could go a little bit earlier if I wanted to. But you know what? No, I'm going to finish. I'm going to finish all the questions that I set out to do here. This is Math 3101A Unit 3 still. Okay, so let's do question 4. So Lexi has 6 identical, boy, what is that? What am I, 12? 6? Lexi has 6 identical black socks and 8 identical white socks loose in her drawer. She pulls out one sock at random and then another sock without replacing her first one. Determine the probability of each event below. Okay, so one reason I wanted to do this one is because it's a good example of how we can use tree diagrams to figure these things out. Now, tree diagrams, I'm not saying 3, I don't mean 3 different diagrams, although, with my accent, you might be confused. I'm going to do tree diagrams, my son. Yes, boy. 1, 2, 3. There's 3 trees over there. Look. Anyway, so I'm going to do a tree diagram because this is a small enough sort of situation that we can represent it with a tree diagram without it like taking up 8 pages of paper. So she has black socks and white socks loose in her drawer. So what's the first event, right? So pulls out a pair of black socks. So we have pull 1. And on the first pull, she's either going to get a black sock or she's going to get a white. Now, I don't think I did this in your courses, Calais, but the first time that we introduced tree diagrams, we just sort of go through them to find the sample space. But here we're not just finding the sample space. Here we're now finding the probability as well. So along with writing in the result, we're going to write in the chance. So she has 6 black and 8 white. So that means in total she has 14. Right? So this is going to be 6 out of 14, which we could call just 3 out of 7. Right? So it's our probability of this branch of the tree is 3 out of 7. The probability of this branch is going to be 8 out of 14, or 4 out of 7. So 3/7 of the time, she goes down this path in the first pull. 4/7 of the time, she goes down this path in the first pull. But she also then does a second pull. Right? So now we just sort of continue our tree diagram over from these guys. You draw those ones out. Get us a Try to make it large enough so that we'll actually have room to write these. That is sort of the perpetual difficulty with tree diagrams, is realizing just how freaking big they're going to have to be by the time they're done, and leaving enough space when you start. So again, we're going to have black and white. We're going to have black and white as the probabilities, right? But now, is it going to be the same probability? Well, of course not, right? Because she's not replacing the sock. Because why would you? Why would you pull a sock out of your drawer, put that sock back in, and then choose from the same set of socks again? The goal is, I assume, to get two socks the same so you can wear two, right? Unless you're a lowly worm from Richard Scarry, who wears one shoe, right? And so I assume lowly worm also wears one sock. That's a deep cut. That's some good primary school literature there for you. Richard Scarry's lowly worm, right? That's some like that's some LeVar Burton stuff there, right? That's some Reading Rainbow. That was good. It's great content. Um, but now, once we go across here, right, in this situation up top here, we've already pulled out one black sock. So there's no longer 14 socks in the drawer, is there? Now there's 13 remaining. And there's one fewer black and one fewer socks. So now this path is now going to be 5 out of 13 across the top here, because we've got 5 remaining black socks and 13 remaining total socks. This white path over here, this one's now going to be 8 out of 13 because all the white socks are still in there, but we still have one fewer sock. So, one fewer socks. Same sort of deal down here, right? If we pulled out a white sock first, all 6 black ones are still in there, but now there's 13 socks in total. So this path is now 6 out of 13. This path down here, this white one, now there's one fewer white socks, so there's 7 in total, and there's still 13 white socks. So now we have what we call our sample space. So the sample space is what we saw before when we did out tree diagrams, as we went through, and we basically just follow every branch of the tree diagram to the end. So here we have black and black, we have black and white, we have white and black, and we have white and white. But now we're looking at our tree diagrams a little bit differently. We're also going to have the probability. And to find the probability on a tree diagram, all we've got to do is multiply along the branches, right? So for this first branch, right, we had 3 out of 7, which was our first one over here, 3 out of 7. This one is going to be 5 out of 13 times 5 out of 13, right? So that's going to be 15 out of 91. That's going to work out to be, I'm not going to do that in my head, about 16.5% roughly. 16.5% chance that she pulls black and then black. How about black and then white? Well, it's going to be 3 out of 7. That was our first one in simplest form. Time 8 out of 13. So that's going to be 24 out of 91. So that is then going to be about 26.4%. Right? And I guess you can probably see what I'm going to do for the rest of these ones here, right? So now I'm going to have 4 out of 7 times 6 out of 13. Lo and behold, that's going to also equal 24 out of 91, as you would imagine, right? Black than white and white than black are going to actually be the same probability in the end, 26.4%. And then white is going to be 4 out of 7 times 7 out of 13. That's going to equal, I mean, the 7 cancels with the 7. That's going to be 4 out of 13. 4 out of 13. That's going to be about 30.8%. And we see, if we take them all and add them together, now I end up getting back to 100.1 because I've rounded up here more often than I've rounded down. So my rounding did end up in me up with being a little bit off in the end. But you'll notice, of course, that if you go back and add all your values together, the total will, of course, get you to 100%. Right? So now with all of this set up, I can very easily answer all the questions that she's asking for. So for part 1 here, probability of 2 black socks, well, we already found that. That's going to be 15 out of 91, which equals about 16.5%, right? And then 2, it asked us for the probability of white and white. Well, we found that as well over here. And that's going to be 4 out of 13, which is going to be about 30.8%. And then pulls out a matched pair of socks that is either both black or both white. So 3 is the probability of white, white, or black, black, right? And remember now what we saw before. That's going to be the probability of white, white, plus the probability of black, black, subtract the probability of white, white, and black, black. Remember from before, right? But we know that there's 0 chance of this, right? She's only pulling out 2, so she can't get 2 white and 2 black. So, conceptually, we can understand that this point is nonsense, because obviously we can't have that happen. But you do remember the formula, right? Probability of A or B is probability of A plus probability of B minus the probability of A and B, right? So to be very thorough, we will include this part here, but we know conceptually that it doesn't make any sense. So it's 0, right? There's no chance that when you pull out 2 socks, you've got a pair of white and a pair of black, right? Come on. So that's going to be 30.8 plus 16.5. I'm just going to not even going to bother with adding the fractions and keeping them in lowest terms and all that sort of nonsense. That's going to be 47.3. So a bit less than half the time. If Lexi randomly pulled out both socks at the same time, would your answer change? Well, no. No, it wouldn't. No, because she still can't pull the same sock twice. She can't pull the same sock twice. So even if she pulls them at exactly the same instant in time, it's not the delay in time that makes this a dependent event. It's the fact that once you've taken one sock, you can't take it again, right? So even if she pulled them at exactly the same split second, we're not saying this is like a double slit experiment where one photon could be in 2 places or something like that, right? This is not we're not talking quantum entanglement here or anything like that. It's not it's not spooky action at a distance. It's just that's a whole bunch of stuff you don't need to know about, but it's interesting. If you want your noodle boiled, look up quantum entanglement. Let me tell you, that's some real science fiction stuff. It's reality and science fiction basically. It's crazy. Theoretical physics is incredible. It's the best topic as far as I'm concerned for science studying. It's the face of God basically. Theoretical physics is it's like looking into the face of God. It's incredible. Anyway, it's beside the point. No, I mean, she still can't pull the same sock twice. If it happens at the same instant, it doesn't matter. It doesn't matter if it's at the same time because she can't get the same thing twice. That's all. Okay, I think that was, boy, oh boy, that was pretty exhaustive, wasn't it? All right, I think we got there in the end. I think we covered that unit in some painstaking detail. So, Calais, I hope that helps you. If you have any questions about that unit, do let me know. But yeah, that was that was fairly exhaustive. Look at those ones, I think. Okay. Yes, thanks for being here with me again on this Friday, while we celebrate this chance to be alive and breathing, as we say, right? Just to quote Maynard James Keenan again a little bit. The song that perhaps has nothing really to do with parabolas, but I love the song anyway. Yes, so thanks for being here with me today. Hope you have a great weekend. Stay safe out there, and I will see you again tomorrow. I will also be interested to see how long it takes my stream to catch up with. I'm a solid, boy, looking at that, I'm a solid 2 minutes behind. Look at that. Anyway, see you Monday.